In this video, we're going to look at angle formulas, angle addition, angle subtraction, and double angle formulas. You'll need to be able to simplify expressions using these, evaluate expressions involving these, and do some proofs involving these identities. The formulas will be on your formula sheet. So first, just looking at this, does the cosine of 75 equal the cosine of 30 plus 45? So we can see here from these values from the calculator that this is not the case. Now we can agree that cosine of 75 can be written as the cosine of 30 plus 45 degrees. So we need to understand that the cosine of a sum is not equal to the sum of the individual cosines. The same is true for sine. So if I do the sine of 75, I get 0.7 here, and then the sine of the sum is 1.21. So these are not equal. So again, the sine of a sum does not equal the sum of the sine of the individual angles. We want to make sure we don't mistakenly use these incorrect formulas. So there are some formulas that we can use for angle sum. So we have a sum for cosine of alpha plus beta. We have a formula for cosine alpha minus beta, and then similarly sine alpha plus beta and sine alpha minus beta. If you would like a proof of these, there's one in your textbook in chapter 5, and it's riveting. So take a look at it if you would like, but we're going to go with, trust me, these are the formulas. These formulas that are in the red boxes here will be on a formula sheet that you will get for the test. From those formulas, we can derive the tangent formula. So starting with tangent alpha plus beta, we can change that into its definition of sine over cosine. So then we can use our angle addition formulas for sine and cosine. So going back to the formulas that we just looked at, we would replace those. And then this is an acceptable formula to use if we want our values in terms of sine and cosine. If we want our values in terms of tangent, then what we do here is we divide everything by cosine, because remember the definition of cosine is sine over cosine. So we divide every term by cosine alpha, cosine beta. So we did that in all 4 places because there was 4 terms to begin with. And then you can see here, like the cosine betas here would cancel out. The cosine betas here would cancel out. The cosine alphas here would cancel out. And that's it. So here we're just left with sine over cosine, which we know is tangent. Here we're left with sine over cosine of beta, which we know is tangent. These cosines also cancel out, so everything cancels out here, so we're just left with 1. And then we have right here, we have the tangent of alpha, and then over here we have the tangent of beta. So that's where this formula comes from. Similarly, over here, we're doing the same thing, but we're using the subtraction formulas. So again, all 4 of these red formulas will be on your formula sheet. All right, so how are we going to use these formulas? So remember, we want to be able to evaluate and we want to be able to simplify. So the first here is doing an evaluation. Find the exact value of cosine of 15 degrees. So normally when we see exact value, we think I need to use my unit circle. So you're looking at your unit circle, but you don't see 15 degrees on there. It has 30 degrees on there, it has 45 degrees, it has 60, but it doesn't have 15. So if we come across a situation like that, we need to take that cosine of 15 degrees in this case, and we need to look around our circle and we need to find 2 values that add or subtract to give us 15. There's always more than one option. It does not matter which one you choose, you just have to come up with one. So looking at your circle, you could say I'm going to use 45 minus 30, I'm going to use 60 minus 45. In this case, there aren't any that you can really add unless you start to use negative values. So I'm just going to use 45 degrees minus 30 degrees. Once I have written that expression that we had there as a sum or a difference, it has to be our sum or difference because those are the formulas we have. Then you can go to your formulas. Remember, they'll be on your formula sheet. So we're going to use the cosine of alpha minus beta. So I'm going to come back here for a minute. I'm going to use this formula, cosine alpha minus beta, because my expression in my parentheses is subtraction and my function that I was using there was cosine. So I'm going to rewrite this using that formula, which is going to be cosine of 45 degrees times the cosine of 30 degrees plus the sine of 45 degrees sine of 30 degrees. So once we get it into this form, then each of these four values is on your unit circle. So you can take a look at your circle. So cosine of 45 is radical 2 over 2 times the cosine of 30, which is radical 3 over 2, plus sine of 45 is radical 2 over 2 again, times the sine of 30, which is 1/2. So then you're just going to do some arithmetic here. So this is radical 6 over 4 plus radical 2 over 4. Notice you have a common denominator, so then we can just make this radical 6 plus radical 2. Remember that we cannot combine radicals through addition or subtraction if they don't have the same number underneath. So now I'm just going to check with my calculator. So I'm going to come here, I'm in degree mode, I'm going to do cosine of 15, and I get the decimal answer. So I can't give this answer because they asked for an exact value, but then I can evaluate this answer that we got. So I'm going to evaluate this. So we're going to do square root 6 plus square root 2 over 4. And you can see I get the exact same decimal answer, so I know my answer is correct. So although you can't use your calculator to get the answer, even on the test you can use your calculator to ensure that you have the right answer. Okay, similar question, except this time we're using radians. So find the exact value of sine 11 pi over 12. Anytime you're doing an exact value where you have to use this procedure, this angle here is going to be in twelfths. So I would suggest that once you have your circle, you just write the equivalent radian values with a denominator of 12 around the circle like I did here. So pi over 6 is 2 pi over 12, so multiplying both by 2. Here I have to multiply both by 3 to get 3 pi over 12. Here I'm multiplying by 4. So when I took the test, if it were me, I would just get my circle and write those twelfths around the circle really quickly, so then I don't have to think about it when I'm in the middle of the problem. So again, I'm going to look at this and I'm going to go, okay, this is sine 11 pi over 12. And I want to look around here and look at these 12ths, and I want to come up with something that's going to give me 11 pi over 12. So I could do 8 pi over 12 plus 3 pi over 12. I could do 9 pi over 12 plus 2 pi over 12. You could also do some subtractions on this one. So I could do maybe 15 pi over 12 minus 4 pi over 12. So it doesn't matter, you just have to find two that are going to work. So I'm going to start with that first one that we came up with. So I'm going to write this as sine 8 pi over 12 plus 3 pi over 12. If you want to reduce those to the pi over 3, if you want to reduce those to the 2 pi over 3 and the pi over 4, you can, or you can just leave them in the 12ths. It doesn't really matter. So remember, now I'm going to use my formula. So I'm doing sine, and this would be sine alpha plus beta. So take a second, look on your formula sheet, and then we're going to use that formula. So this is going to be sine 8 pi over 12 cosine 3 pi over 12 plus cosine 8 pi over 12 sine 3 pi over 12. So again, now I can go to my circle and I can get those values. So here at 8 pi over 12, my sine value is radical 3 over 2 times the cosine of 3 pi over 12. 3 pi over 12 is here, so my cosine value is radical 2 over 2 plus the cosine of 8 pi over 12 is going to be the negative 1/2, and then times the sine of 3 pi over 12, which is radical 2 over 2. So again, now I'm going to just do the arithmetic. So we get radical 6 over 4 minus radical 2 over 4. And then again, I can combine those together. This is radical 6 minus radical 2 over 4. And again, you can see from a check of the calculator that my answer is correct. All right, this next example is similar, except that it's tangent. So we have to use the different formulas now. And we still have a radian measure here, so we need to come up with that in the twelfths again. So tangent 5 pi over 12 is, so let's do tangent 5 pi over 12 equals tangent of 3 pi over 12 plus 2 pi over 12. So now go to your formula sheet. We're going to do tangent formula, and then this is alpha plus beta. You have that formula in sine and cosine, or you also have it in terms of tangent. It doesn't really matter which one you want to use. It's just a preference. I'm going to use the tangent formula. So if we rewrite this as tangent 3 pi over 12 plus tangent 2 pi over 12 over 1 minus tangent 3 pi over 12 times tangent 2 pi over 12 Please notice that this is multiplication here. A lot of people make the mistake of putting a plus sign in there, which is going to make your answer wrong. So pay attention to your formula and notice that that's multiplication. Okay, so now here, in order to fill these in, we have to know our tangent values. So remember, your tangent values here is undefined. This is radical 3. This is 1. This is radical 3 over 3. So tangent of 3 pi over 12 is 1, plus the tangent of 2 pi over 12, this is radical 3 over 3, divided by 1 minus tangent of 3 pi over 12, remember, is 1, times radical 3 over 3 again. All right, so now this is all just arithmetic here. You got to remember a bunch of things from Algebra 2 about radicals and fractions. So we need to simplify this. The first thing I'm going to do is just simplify this denominator, multiply this out. So I got 1 plus radical 3 over 3 over 1 minus, and then I'm just multiplying this together. So this is radical 3 over 3. The next thing I'm going to do is get rid of the fractions within fractions. So my denominator on both of these is 3. So we're going to multiply every term by 3, which is going to give us 3 plus radical 3 over 3 minus radical 3. So that is an acceptable answer unless you are requested to rationalize the denominator. So this is an answer. This is a simplified answer. Again, unless they're asked to rationalize. If you're asked to rationalize, then remember we're going to multiply by the conjugate of the denominator. So I'm going to multiply by 3 plus radical 3 over 3 plus radical 3. So here, foiling the numerator, we get 9 plus 3 radical 3 plus another 3 radical 3 plus 3. And in the denominator, we get 9 plus 3 radical 3 minus 3 radical 3, and then minus 9. In your denominator, the radical term should cancel out. And then here, we're going to have 9 plus 3 in the numerator, which is 12. And then I've got 3 radical 3's and 3 more radical 3's, so I've got 6 radical 3 over. And then in my denominator, I just have 9 minus 3, which is going to give me 6. So remember, if your radicals from your denominator are not all gone, then you did something wrong. In the numerator, I'm going to factor out a 6, and then I can cancel the 6's. And we have our answer, which is 2 plus radical 3. And then again, a check of my calculator shows that I do have the correct answer. Okay, so the next question is just asking us to simplify. So here we're just really looking to match the expression we have up with something that's on our formula sheet. Typically when you're simplifying, you're going to be going from the right side of an expression to the left side of the expression. So if we think of this and notice that I have angles that are the same, so I have 22 degrees there, and then I have 13 degrees here. So if I think of the 22 degrees as alpha and the 13 degrees as beta, I should be able to look at my formula sheet and be able to find an expression that has sine alpha cosine beta plus cosine alpha sine beta. And that is equivalent to sine of alpha plus beta. So in this case, remember my alpha is 22 degrees, my beta is 13 degrees, so this is sine of 35 degrees. And that's my answer. So I'm just trying to simplify it into one expression if possible. Okay, so similarly on this one, we have cosine pi over 3, and then I have a pi over 3 over here, and then I have cosine pi over 4, and then I have pi over 4 over here. So I've got two different arguments, a pi over 3 and a pi over 4. So again, I'm going to think about this as alpha, and I'm going to think about this as beta, and then I'm going to look at my formula sheet. Where do I have cosine alpha, cosine beta, plus sine alpha, sine beta? And that should look similar to cosine alpha minus beta. So then I'm going to do cosine pi over 3 minus pi over 4. We need to actually do this, so we need a common denominator. So this is 4 pi over 12 minus 3 pi over 12. So this is cosine of 1 pi over 12. And then again, that's my answer. Here we're doing a proof, so we have to go through the proving process. So I have cosine pi over 2 minus theta equals sine theta. So I'm going to start with this left side because it looks a little bit more complicated, and I'm going to try to get it simplified to the right side. So what I notice here is that I have a cosine of difference. So if I think about my formula that says cosine alpha minus beta, so I'm going to use that formula. So I'm just going to rewrite this using that formula. So cosine of pi over 2 times the cosine of theta plus sine pi over 2 sine theta. And we want that to equal the sine of theta. Then pi over 2 is on my circle, so I can go and I can take a look at my circle. The cosine of pi over 2 is my x-coordinate, and that's going to be 0. So this is going to be 0 times the cosine of theta plus, and then my sine value at pi over 2 is 1. 1 times the sine of theta. So this is just 0 plus the sine of theta. And we got sine of theta equals the sine of theta. Okay, so the other formulas that we need to work with are our double angle formulas. So you can kind of see here I derived those double angle formulas. So the sine of 2 theta is just sine of theta plus theta. So using our formula for that and simplifying, we get the sine of 2 theta is 2 sine theta cosine theta. So there's only one formula for the sine of 2 theta, but down here where we do the cosine of 2 theta, we actually have 3 different formulas. So using this formula, we get cosine theta times cosine theta, which gives us the cosine squared theta, and then minus sine squared times, or sine times sine, which gives us sine squared. So my first formula for the sine of 2 theta is cosine squared minus sine squared. And then using my Pythagorean identities, we can find 2 more formulas. So if we start with this original formula here, cosine squared minus sine squared of theta, then I'm going to replace cosine squared with 1 minus sine squared, and remember that's from my Pythagorean identities. And then just simplifying this gives me 1 minus 2 sine squared theta. And then the same thing over here. If I start with this same original equation that we had here, I replace the sine squared with 1 minus cosine squared from my Pythagorean identities. We get cosine of 2 theta is 2 cosine squared theta minus 1. So all 3 of these are possibilities for the cosine of 2 theta, and all 3 of them will be on your formula sheet. Similarly, we've got some formulas for the tangent of 2 theta. So you have one formula in terms of sine and cosine, and we have another formula in terms of tangent. So again, both of these are on the formula sheet, and you just choose whichever one you need to use depending upon what information you have. So again, if we're simplifying here, we have sine x times sine 2x minus cosine x times cosine 2x. So I have, again, if I think of this as alpha, and if I think of this as beta, then I can start here. We have sine times sine minus cosine times cosine. So I have something similar on my formula sheet, except it has cosines first and sines second. So I need it to look exactly like what's on my formula sheet before I can use my substitutions. So I'm going to rewrite this for a minute here, and I'm going to make this negative cosine of x, cosine of 2x, plus sine of x, sine of 2x. So now the cosines and the sines are in the right position. However, this negative sign out front is a bit of a problem. So we're going to factor out the negative. So once I factor out the negative, I get cosine times cosine minus sine times sine. And that's exactly the way it is on my formula sheet. So now I can use the substitution. This is cosine alpha plus beta. So this would be cosine x plus 2x. So I get negative cosine of 3x. So I end up with negative cosine of 3x. Similarly, here we've got another proof again. So here I've got cosine to the 4th x minus sine to the 4th x. So this is a perfect square. Sine to the 4th and cosine to the 4th are perfect squares, and it's a subtraction in between them. So I'm going to use difference of 2 perfect squares, and I'm going to write this cosine squared x plus sine squared x, and cosine squared x minus sine squared x equals the cosine of 2x. So again, remember, we're just using the difference of 2 perfect squares here. So I'm using a squared minus b squared equals a plus b times a minus b. Just in this case, we have 4th powers, which when we square root them, we get squared. So this first expression is just the Pythagorean identity, which is just 1. This second expression, cosine squared theta minus sine squared theta, is equivalent to cosine of 2 theta, which is what we have on the other side, which is what we're trying to get. So we have cosine of 2x equals cosine 2x. I said theta before, sorry, it should have been x.